We're going to look at the topic of optimization problems, which are a lot of the time called max-min problems in calculus. So these are ideas where I'm trying to maximize or minimize some value, so I have an optimal or efficient use of surface area, volume, space, things like that. We're going to start with a question that is basically a grade 11 problem. We've done these before, but we're going to use a calc to do it. So I want to find the area of the largest rectangle that has a perimeter of 200 feet. So I want to maximize some of these values, right? I want to maximize area, biggest rectangle I can possibly make, but I have some limiting factors. I have some other contextual information. I only have a perimeter of 200 feet to work with, so I have some limitations here. Well, first, what do I know, right? I'm dealing with a rectangle. Here it is, 2 lengths side x, 2 lengths side y. I don't know how long any of these sides are going to be. That's my goal, right? I want to figure out what x and y give me the biggest rectangle. Is it going to be something that looks like this? Is it going to be something that looks like this? Is it going to be some middle ground, right? That's what we're trying to figure out using calc. So if I want to talk about the area of the largest rectangle, I'm going to make an equation. This is called my primary equation, which is the equation that I'm actually dealing with maximizing the value, right? I'm dealing with area. This is my first or my primary equation. But right now it has too many unknowns, and they gave me other context. They told me separately that the perimeter was 200 feet. And I know from working with rectangles that the perimeter is equal to just all of those side lengths combined, so 2 x's and 2 y's. So this is going to be my secondary equation, right? I'm not trying to maximize perimeter. I have that as a set value. It's a constant value. Technically, I could make it less, but that's not going to lead to a bigger rectangle. And so this is going to help me work with A a little better. I have a system of equations because they're talking about the same values of x and y, right? The same x being length, y being height of the same rectangle. Now I can manipulate this equation and make it my equation I'm more used to. I can isolate y. I can call this 100 because everything is 2 times too big, minus x equals y. And now I have a better way to describe x and y. Now, something we're going to do a little different is we're going to look at the restrictions here. I need to think about my restrictions, my domain on x, my potential range for y. Well, my domain on x is that x, first of all, has to be greater than or equal to 0, because I can't have negative lengths. But there's also some maximum value that x can be too. And I know that because 100 minus x is equal to y, I know that this second situation, my range here, can be replaced by saying 100 minus x also has to be greater than 0. And so x has to be less than 100. And that makes sense. Because if I had 2 lengths where this was 100 and this was 100, I would have used my entire perimeter, right? I don't have anything left. And so that's my cap out, my maximum value of x there. What that gives me is that gives me a closed interval, a restricted domain, where x is between 0 and 100. Which we're going to see help us out in a sec here, using what we know about calculus. So anyway, I'm going to go back to my primary equation. My first one, area is 100, or area is x times y, sorry. Now, too many variables, a, x, y, all three of those are different dimensions or different properties about this rectangle. But I can also now say that area is x times 100 minus x. I'm using my system of equations to substitute in the fact that this is equal to y, so let's replace y with it. So my area is 100x minus x squared. So now I want to find the maximum of this equation. Well, we've done this in calculus before. Maximum, I'm going to look for local maxes and mins. Because I'm on a closed interval, extreme value theorem tells me there has to be a max or a min within this interval here, right, between 0 and 100, either at a local max or min, and so I'm going to take the derivative, work with that, or I'm going to check my endpoints. So that's super important here. The endpoint could be a max or a min. Now, using our calculus, how do I find the maximum of a value? Well, maximum happens when my derivative is equal to 0 or does not exist, right? Those are the only locations I could find a local max or min. Again, maybe it's one of the endpoints. Maybe I have no local max or mins. We know enough about quadratics to know that we do, but the calculus is going to help us out. So let's look at my derivative here. The derivative of a is going to be 100 minus 2x. I'm now going to solve for when this is equal to 0, because this thing will never not exist. Bring the 2x to the other side and divide by 2, x equals 50. So this is where I have a local potential max or min, maybe. It's just a critical point for now. Right? I have a critical point. I don't know if it's a max or min or neither. Need to check my intervals. So when I'm making my number line this time, though, I have a closed interval. I know this thing only starts at 0 and can go up to a maximum of 100 in terms of x, my independent variable. And I know that my critical point in this case happens to be right in the middle. And so I want to ask myself, what's happening to a prime? What are the signs on a prime to tell me if I have a max or a min on a itself? And so I'm looking at values in between. When I pick a value between 0 and 50 and plug it back into my original a function, right? Or sorry, plug it into my a prime function, a number like 1, 100 minus 2 times 1 is still going to put me in the positives. So a prime, or original area, is increasing. A number bigger than 50, so something like 75, 51, whatever, is going to spit out a negative. 100 minus 102, right? Overall negative. So my function a, let me just rearrange this. A prime is up here. This is the resulting increase or decrease of a. Tells me that because I'm seeing that change from increasing to decreasing, I do have a maximum at x equals 50. Right? And then technically I should find that y value, but we'll check in a sec. So I have a maximum at x equals 50. I also want to check my endpoints, right? Again, a little bit of a different concept. We haven't done this as much with our curve sketching because we've been working on open intervals for the last while. Now that I'm working on a closed interval, I need to check my endpoints. So I'm going to check my area at 0. I'm going to check my area at that max of 50 and see, is that my absolute maximum? I'm going to check my area at 100 and say maybe those endpoints are larger. Well, when I plug 0 into a, it's 0 times 100 is 0. 50 into a, right? I'll show you what I'm writing out. X times 100 minus x. I'm going to go into the factored form here just because it's a little cleaner to work with. Do the math a little quicker. When x is 50, 50 times 100 minus 50 is 50 times 50 is 2,500. And lastly, 100 is 100 times 100 minus 100 is going to give me another 0. So in this case, extreme value theorem tells me that 2,500 is my maximum area given an input of x. So I can state it, max area of 2,500, give me some units, feet squared. And that happens when x is 50 feet. Right? I could go through, plug it back into my system to tell you that this also happens when y is 50 feet. But we're mainly going to focus on that independent variable here, depending on what the question's asking. Right? It didn't ask me for the dimensions, it just wanted the largest area. So I gave you largest area. So when it comes to these types of problems, here's your guidelines, here's your rules. I'm going to identify all given quantities, so things that they tell me in the question, right? They gave me perimeter that last time. And all things that I need to find. So in this case, it was maximizing area. If you can't, draw it out. It's going to help you out. I'm going to write a primary equation for the quantity to be maximized or minimized. So ask yourself, what is the question asking you to maximize or minimize? In that case, it was area. So I need to talk about the area of a rectangle as my main focus, right? That perimeter helps me deal with that area formula, get it into less variables. But at the end of the day, I'm talking about area, not perimeter. And you're going to use lots of your regular surface area, volume, Pythagorean formulas for these. You're going to reduce the primary equation to having one single independent variable. Again, you're going to basically use your secondary equation. And so that's what they gave us with perimeter, right? Sometimes it's just a value, sometimes it's an equation relating those independent variables. Making a system of equations. Ooh, wrong pen. System of equations. Because I have two different equations, but they're talking about the same x and y. Right? Area here is talking about x and y just through multiplication to get the surface area. Perimeter is talking about the same x and y, but giving me those outside one-dimensional lengths. Again, this is big. This is a little bit different for us. I need to think about the feasible domain of my primary equation, right? So think about what values of x, right? What are my independent variables? What values am I allowed to be working with? Because I need to be using extreme volume theorem tells me that max or min might not actually be the local max or min. I'm talking absolutes here. And then we're going to find that max or min using calc techniques, right? So take the derivative, set equal to 0. If it's rational, check when it doesn't exist either, because those are how I find those local maxes and mins. Right, and then last part, so extreme value theorem. We went through this in our last unit. Check the critical numbers and the endpoints. Endpoints, critical numbers. Oh. Right, so checking both locations. All right, let's try a few more of these. So a manufacturer wants to design an open box. So key idea here, this is not a part of my surface area. Having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume? So here we are, primary equation. What do I want to maximize? Volume. Volume of a cube is length times width times height. Using the variables we have here. They told me it has a square bottom, so length and width are both x. My height is height. So my volume is x squared h. So this is what I'm going to be working with. This is what I'll take the derivative of. This is where I'll check for my critical points and endpoints involving x's and h's. My secondary equation, they tell me information about surface area. So the surface area of this box, well, it's going to be that base, which is x times x, which is x squared. And then it's going to be, right, so this is x times x. And then it's going to be those four sides that are h times x. So my surface area is x squared for the bottom plus 4xh. If this had a closed top, I would have two of those x squared sides, but I don't have an open, right? It's an open box. There's no top to it. So again, secondary equation, not what I'm maximizing, not what I'm going to take the derivative of, but quantities that I'm going to work with to help essentially get volume into one variable instead, or two variables instead of three. So they tell me surface area is 108. I want to essentially use this to isolate one of my variables. And I'm going to isolate h because I'd like to work with x's, keep things in that independent variable. So I bring that x squared to the other side. I divide both sides by 4x, and I'm left with h. So moving forward, now I'm looking at the equation volume is x squared times 100 minus x squared over 4x. Now, if I'm going to take the derivative of this thing, I want to clean things up a little bit. I want this to be less work for me to deal with before I take the derivative. So I'm going to simplify. I'm going to multiply these things together. I have an x squared times an x on the bottom here, so I can at least simplify that way. Volume is going to be 100x minus x cubed all over 4, because I'm just multiplying x into the numerator, those two terms. And again, I'm going to distribute because taking the derivative of the terms is easier than taking the derivative of a product. It would be even easier if I didn't have a fraction. And so I'm going to rewrite this. Oops, sorry, that's 108, not 100. There we go. So I can go even further and call this 27x, so divide the first side by 4, minus 1/4 x cubed, just so that I don't have to worry too much about doing any sort of weird chain rule or pulling out a factor of 1/4 through the whole thing. All right, taking my derivative, v prime 27 minus 3/4 x squared. Now, extreme value theorem, checking those critical points, checking those endpoints to find my absolute max or min. Let's find the local first. Let's say when is v prime equal to 0? Right, so what is the solution to this quadratic equation? I'm going to bring things to the other side. 3/4 x squared equals 27. X squared is 27 times 4 divided by 3 is going to be 36. Square root both sides, x is going to be plus or minus 6. Those are the solutions to this equation. Now let's think about the interval that this works on. Negative isn't going to make any sense. So already that's not going to be a critical point that I check because it's outside my domain. My domain is going to start from 0 because I can't have less than 0 for my side lengths. I have a critical point at 6, somewhere along the middle. And then my maximum value is going to come over here, where I know that height also has to be greater than or equal to 0, because I can't have a negative height. But again, I'm going to use that in terms of x. So 108 minus x squared over 4x has to be greater than or equal to 0. Solving this inequality, I can multiply both sides by 4x. It kind of just disappears. So 108 minus x squared is greater than or equal to 0. X is going to be less than the square root of 108. Right, technically plus or minus, but again, because I'm talking about where it's greater than 0, I'm looking at the positive case. So x is less than the root of 108. So that's going to be my other endpoint for values that are possible for x. And that would essentially be, that would be the case where I have almost no height and my base is the entire length, right? Root 108 times root 108 along the base here would give me a whole surface area of 108 coming entirely from the bottom. So that's my maximum value for x. So 108. So first of all, I want to make sure that 6 is actually a maximum. Again, we don't want to just assume that a critical point is a maximum and then check it. So my volume between 0 and 6 is going to give me in v prime, the derivative of my volume is going to give me a positive value because I'm subtracting. When I choose numbers that are between 6 and 108, that's where I get negative results. So yes, I swap from increasing to decreasing. I know I have a local maximum at 6. I'm going to quickly check. I'm running out of room here. I'm going to check volume at 0. I'm going to check volume at 6. And I'm going to check volume at the square root of 108. And then whichever is my maximum value here is my absolute maximum. And so volume at 0 is 0, right? I'm just plugging that into my volume equation. Volume at 6 is going to give me 108, right? So I'm doing 108 times 6 minus 6 cubed divided by 4. Volume at root 108 also gives me 0, but again, that's not always going to be the case. And then the question, we just go double check. What did we get? What dimensions will produce a box with maximum volume? Well, this dimension told me x equals 6, and our units are inches. I should also find h. So I'm really going to quickly just go to my surface area formula or my volume formula and solve for my last unknown. Ideally, I'm going to plug it in here because I already know x. So h is 108 minus 6 squared over 4 times 6, right? Because I've already decided the x value that gives me maximum surface, or give me a surface area of 108, maximum surface area. The h value, the related value of 108 minus 36 divided by 24 ends up also giving me 6. And so my dimensions are an x value of 6 inches, a height of 6 inches. So 6 times 6 times 6 gives me that surface area of 108. And that happens to be the largest volume. It is not going to be more optimal or more optimized if I make this shorter with a bigger base, or if I may shrink the base and make this taller in this case. So let's look at a different way we can kind of use these ideas. Find a minimum difference. So instead of maximizing or minimizing a surface area volume, let's talk about a minimum difference. What points on this graph are closest to the points 0, 2? Right, so there are some points along this where the distance between, the straight distance between this point and this point is the smallest. Length D is the shortest. Because anywhere else, maybe I'll put a point, distance is longer. I put a point down here, distance is longer. Even slightly nearby, because we're dealing with lines at different angles, it might be slightly longer. So I'm trying to minimize something, I'm still using optimization. So same idea here. I want to start with a primary equation. What am I maximizing or minimizing? I'm maximizing or minimizing D, my distance. And so my primary equation, I want to minimize D. My equation for D, if you remember a distance equation, you might remember this from physics, or we've looked at it briefly in math before. If I want to find the distance between 2 points, it's x2 minus x1 squared plus y2 minus y1 squared, right? And that comes from Pythagorean triangle, rise over run, those kinds of ideas. And so here I know some of those. I have x and y. I also have x1 and y1 as values. So here's my equation. The distance is the square root of x minus 0 squared. So I'm just going to go ahead, cheap out, write x squared plus y minus 2 squared. This is what I'm trying to maximize or minimize. This is what I'm going to take the derivative of. Right now, I have a problem. Don't really want to do implicit. I don't need that x and that y. So what else do I know? Well, I know an equation already. So here, my secondary equation was already given to me. How nice is that? So I'm going to go ahead and plug it in because this is equal to y. So now my distance is the square root of x squared plus 4 minus x squared minus 2 squared. I'm going to clean this up a little bit before I take that derivative. And so D is going to be x squared plus, it's going to look like a 2 minus x squared squared. So let's take the derivative. Let's look for those local maxes or mins. Again, I'm not talking about this. I'm not talking about this max or min. I'm not talking about the max or min of my single equation. I'm talking about the max or min of this length value. So D prime looks like, well, I'm actually starting, I'm going to rewrite this as a power to make my life a little bit easier. X squared plus 2 minus x squared squared. I'm going to leave it in this factored form just so the chain rule helps me out. And I'm not distributing a binomial and wasting my time. All that to the power of 1/2. So when I take my derivative, outer chain rule, bring down that 1/2, leave everything inside alone. X squared plus 2 minus x squared squared. Now that goes to the negative 1/2 times, take the derivative of the inside, 2x plus, now I have a little bit more chain rule here. Bring down my power to 2 minus x squared times derivative of the inside is a negative 2x. Rewrite this as a denominator and simplify things a little bit here. So I'm going to move this to my denominator on the bottom here. I have a 2 from that fraction 1/2. I also have a square root of x squared plus 2 minus x squared, all squared. On the top, I have this whole second factor. I'm going to take a quick step and factor while I'm here. My two terms both have a 2x, so I'm going to pull out a 2x. I'm going to be left with a 1 plus 2 bracket 2 minus x squared, which is all times a negative 1 now because I factored that out. So I'm actually going to go back in. I'm going to just swap this to a negative sign because of this negative here. So I'm going to simplify a little more. So I can reduce that common factor of 2 out front. I can call this x. I can call this 1 minus 4 plus 2x squared by distributing this minus 2 into both of those terms there, over the square root of x squared plus 2 minus x squared squared. And then lastly, simplify that top a little bit. It's going to be x times 2x squared, because that's positive, I'll write it first, minus 3, because I have 1 minus 4, over the square root of x squared plus 2 minus x squared squared. And there's my derivative. What am I using that for? Finding my critical points. Let's find our critical points. Critical points happen when d prime is equal to 0, or when d prime does not exist. Well, when is it equal to 0? It's equal to 0 when x times 2x squared minus 3 equals 0. So it's equal to 0 when x equals 0, or when x equals, isolating here, 2x squared minus 3 equals 0, x equals plus or minus the square root of 3 over 2. D prime does not exist when the square root of x squared plus 2 minus x squared squared equals 0, which if we look is not going to happen because this is going to be a positive term every time. I'm adding to that a positive term every time, and I'm taking the square root of a positive, which is positive. So I can never get that to equal 0, right? It's going to be two big positive, or even small, two positive numbers added together. Square root of that is going to be bigger than 0. So these are my critical points. These are the places I'm going to check. I'm looking for a minimum here. So let's think about those minimums. So, looking on my number line, I'm concerned about what's happening at negative root 3 over 2. And again, this time I'm allowed to have negatives because I'm looking at an xy plane. I can have negative x values. It just means I'm moving to the left. So I'm checking those negative 3 over 2s. I'm checking those zeros. I'm checking those positive root 3 over 2s. And in this case, I don't really have a closed interval this time, so I'm not going to worry about these endpoints as much, right? I don't have any limiting factors on distance because this graph will go on forever. I'm going to compare what happens between d prime, the distance derivative, and d. I'm going to look at a few values. So when x is less than negative 3 over 2, so maybe it's some value like x equals negative 2, something like that. I'm checking it in my derivative function. It's going to be negative number times, if I have something less than negative 3 over 2, it's going to give me a positive here, so I get a negative on top. And then on the bottom, as we talked about, that's always going to be positive. So I start off with a negative interval, so I'm decreasing for d. If I move between negative root 3 over 2 and 0, so that's the case where now I still have a negative number, I still have a negative number here for this factor, but I'm also going to get a negative number here because I'm subtracting 3. That first term will be smaller. So I get positive over positive. Again, that denominator will always be positive, so I'm increasing. So I have a minimum value here. Between 0 and root 3 over 2, I'm going to get another negative. Bigger than root 3 over 2, I'm going to get another positive. And so I see that change in values over and over. What that tells me is that x equals negative root 3 over 2 is a minimum. This tells me that x equals 0 is a maximum. And it tells me that positive root 3 over 2 is another minimum. And because we're on an open interval, we're just assuming local, not absolute. So because I have two minimum values, I'm going to check the y values at both. And that is going to tell me those 2 points, right? Those are going to be the points to the left and to the right that give me that shortest distance. And they're equidistant, right? They're the same distance away, which is why they're both showing up as a minimum, because that's the point where d is the same smallest value. I'm going to find those points. So closest points are that root 3 over 2 and positive and negative. X equals positive root 3 over 2, all under one radical, is going to show up. I can plug it into either of my two original formulas, either my primary or secondary. Secondary is going to be easiest in this case, so I'm going to plug it into there. But again, both of these are talking about x and y. I'm going to plug it into that secondary equation. So y equals 4 minus x squared, root 3 over 2 squared is going to be 4 minus 3 over 2, which is going to simplify to about 2.5, right? It's going to be 8 minus 3, so 5 over 2. Same thing is going to happen when x is negative root 3 over 2. Y is 4 minus negative root 3 over 2, but because it's squared, it sets out the exact same value of 2.5. So closest points, are at, I'm going to say negative root 3 over 2, comma 2.5, and positive root 3 over 2, 2.5. All right, so quick recap. Again, with these optimization problems, step 1, think about what you're trying to be maximizing or minimizing. Step 2, use the information. You have some secondary information to make yourself an equation with less variables, less unknowns, right? Make a system. And then lastly, you're finding those maxes and mins using our curve sketching techniques, right? Check that f prime of x to decide if f of x is increasing or decreasing and where I see that change, right? And then also making sure that we're checking endpoints if we're on a closed interval. We'll look at some examples where we can decide how to find that closed interval next time.